Imagine standing at the edge of something impossible, not the edge of a cliff or the shore of an ocean, but the edge of existence itself, a boundary where the rules that govern everything you've ever known simply stop working, where time bends, space tears, and light itself cannot escape. This is the realm of black holes, and tonight we're going to explore these strange horizons together. What really happens at the edge of a black hole? It's a question that has haunted physicists for more than a century, ever since we first realized that such objects could exist. Does anything truly escape their grasp? For decades, we thought the answer was a simple no. But as our understanding has deepened, we've discovered that black holes are far more complex, far more mysterious than we ever imagined. You've probably heard of black holes before. They're the monsters of the cosmos, the ultimate cosmic vacuum cleaners, objects so dense that they warp the fabric of reality around them. But beyond these dramatic descriptions lies something even more profound. Black holes are places where gravity doesn't just pull strongly, it becomes absolute. It becomes the only force that matters. Everything else, every other law of physics, must bend to its will. Tonight, we're going to take a journey together to understand these extraordinary objects. We'll explore how they're born in the violent deaths of massive stars. We'll stand at the edge of the event horizon, that famous point of no return, and try to understand what it really means. We'll delve into how black holes warp spacetime itself, bending the very fabric of the universe into impossible shapes. And then we'll venture into even stranger territory, exploring the theoretical predictions that black holes might not be eternal after all, that they slowly evaporate through a process so subtle it takes longer than the current age of the universe. Finally, we'll peek beyond the edge of our current understanding into the realm of speculation and possibility. Wormholes that might connect distant parts of the universe. White holes that could be the time-reversed twins of black holes. And the fundamental questions that remain unanswered, waiting at the boundary where our best theories break down. This is a journey into the extreme, but I promise to guide you gently. We'll take our time. We'll let these vast ideas settle slowly, like snow falling on a quiet winter night. Because understanding black holes isn't just about grasping exotic physics. It's about confronting the limits of human knowledge and finding a strange kind of peace in the vastness of what we don't yet understand. So settle in, get comfortable, let your mind expand to encompass these cosmic mysteries, and let's begin our exploration of black holes where gravity becomes absolute. The violent birth when stars surrender. Every black hole begins with a star, not just any star, but a massive one, at least 8 times more massive than our Sun, and often much larger. These stellar giants burn bright and hot, fusing hydrogen into helium in their cores, generating the tremendous outward pressure that keeps them from collapsing under their own gravity. For millions of years, they maintain this delicate balance, a cosmic dance between the inward pull of gravity and the outward push of nuclear fusion. But nothing lasts forever, not even stars. Imagine you could watch one of these massive stars throughout its entire lifetime, compressed into just a few minutes. For most of that time, you'd see it shining steadily. A brilliant beacon in the darkness, hydrogen fuses into helium, releasing energy that streams outward, keeping the star inflated against gravity's constant squeeze. But as the hydrogen in the core runs out, something has to change. The core contracts, heats up, and begins fusing helium into carbon and oxygen. The star adjusts, often swelling into a red supergiant. This pattern continues, each new stage burning faster than the last. Carbon fuses into neon, neon into oxygen and magnesium, oxygen into silicon, and finally, silicon fuses into iron. At each stage, the star's core becomes denser, hotter, more desperate in its fight against collapse. But iron is the end of the line. Fusing iron doesn't release energy, it consumes energy. When the core fills with iron, the star's fate is sealed. What happens next occurs so quickly that if you blinked, you'd miss it. The core, no longer supported by fusion, collapses. In less than a second, a region larger than Earth compresses to a sphere perhaps 20 kilometers across. The collapse happens so fast that the outer layers of the star don't even know it's occurred yet. They're still falling inward when they encounter the unimaginably dense core, and the collision releases more energy than the star emitted during its entire previous lifetime. This is a supernova, one of the most violent events in the universe. The explosion is so bright it can briefly outshine an entire galaxy. Heavy elements, gold, platinum, uranium, are forged in these final moments and scattered across space, eventually becoming part of new stars, new planets, perhaps even new life. But at the center, hidden beneath all that fury and light, something even more extreme may be taking shape. If the collapsing core is massive enough, nothing can stop it. Not even the force that keeps neutrons from occupying the same space. There's a limit to how much mass a neutron star can support, a threshold called the Tolman-Oppenheimer-Volkoff limit, named after the physicists who first calculated it. The exact value is still uncertain, somewhere between 2 and 3 times the mass of our Sun, but the principle is clear. Below this limit, the collapse halts. The core becomes a neutron star, an object so dense that a teaspoonful would weigh as much as a mountain on Earth. But above this limit, nothing halts the collapse. The neutron degeneracy pressure, the quantum mechanical force that keeps neutrons apart, simply isn't strong enough. The core continues to shrink. 20 kilometers across becomes 10, 10 becomes 1. The density climbs beyond anything we can truly comprehend, and somewhere in this process, the collapsing core crosses a threshold from which there is no return. It becomes a black hole. Here's what's remarkable. We're not entirely certain about all the details of this process. For a long time, scientists assumed that all stellar black holes formed in spectacular supernova explosions. But recent observations have shown that massive stars can sometimes collapse directly into black holes without producing a bright supernova at all. They simply disappear, quietly surrendering to gravity without fanfare. Astronomers have studied a binary system called VFTS 243, located in the Large Magellanic Cloud, a small galaxy near our own. They found a black hole orbiting a massive star, but the orbit was almost perfectly circular. If the black hole had formed in a violent asymmetric supernova explosion, the blast should have kicked the black hole to high speed, disrupting the orbit. Based on this observation, researchers interpret the circular orbit to suggest something different. The star likely collapsed into a black hole with minimal explosion, releasing its energy primarily through neutrinos rather than light. In such a collapse scenario, the energy would be released in the form of neutrinos, nearly massless particles that interact so weakly with matter that they stream through the collapsing star almost unimpeded. To an observer watching from a distance, the star would simply fade away, dimming over days or weeks, as if someone were slowly turning down a cosmic dimmer switch, and then, suddenly, it would be gone. In its place, a black hole, born not with a bang, but with barely a whisper. There's another way for black holes to form, one that we've only recently been able to observe directly. Neutron stars, those incredibly dense remnants that form when stars aren't quite massive enough to create black holes immediately, can merge with each other. When two neutron stars spiral together, their mutual gravity tears them apart in the final moments before collision matter erupts from the collision point, creating a brief flash of incredibly hot material. And then, in just milliseconds, if the combined mass exceeds that crucial limit, the merged object collapses into a black hole. In August of 2017, gravitational wave detectors felt the spacetime ripples from just such a collision, an event designated GW 170817. The detectors measured the increasing frequency of gravitational waves as two neutron stars spiraled together, each orbit faster than the last, until finally the signal cut off abruptly. Telescopes around the world swung to point at the source and caught the afterglow, a kilonova powered by the radioactive decay of heavy elements forged in the collision. Analysis of the observation suggests that the merger produced either the most massive neutron star ever observed or, more likely based on theoretical models, a black hole. Think about the timescales involved here. The original stars may have lived for tens of millions of years. The neutron stars may have orbited each other for billions of years, slowly spiraling inward as they radiated gravitational waves, but the actual collapse into a black hole, whether from a supernova or a merger, takes less than a second. Often much less, a tenth of a second, a hundredth. In that brief instant, matter is compressed beyond the point where any known force can resist, and a new black hole is born. What determines whether a collapsing core becomes a neutron star or a black hole? Mass is the primary factor, but it's not the only one. Rotation matters. A rapidly spinning core can support slightly more mass before collapsing. Magnetic fields play a role. The exact composition of the core affects how it responds to compression, and there are still uncertainties in the physics at these extreme densities. We're describing matter compressed far beyond anything we can create in laboratories on Earth, far beyond the density of atomic nuclei. Some physicists theorize that quarks, the fundamental particles that make up neutrons and protons, might be liberated at these densities, forming what's called a quark star. Whether such objects are a distinct phase or simply a step on the way to black hole formation remains an open question in theoretical physics. But once the collapse begins in earnest, once the core passes that threshold beyond which no force can stop it, the outcome is inevitable. The matter continues to compress. The gravitational field grows stronger and stronger, and somewhere in this process, the collapsing matter crosses a boundary. From the outside, this boundary is invisible, marked by no physical structure, but it's one of the most important concepts in all of physics. This is the event horizon, the point of no return, And once matter crosses it, that matter is lost to the outside universe forever. The birth of a black hole is violent, yes, but there's something almost peaceful about the end result. After all the fury of collapse, after the tumult of supernova or the chaos of merger, what emerges is, in some ways, the simplest object in the universe. A black hole can be completely described by just three numbers: its mass, its electric charge, and its angular momentum. How fast it's spinning everything else, all the complex details of what fell in to make it, is erased. Hidden behind the event horizon, the information about the original matter is locked away, perhaps forever. This leads to what physicists call the no-hair theorem, a somewhat whimsical name for a profound idea. Black holes have no distinguishing features beyond those three properties: no hair, no surface features, no individuality in the conventional sense. And yet, despite this simplicity, black holes remain among the most mysterious objects in the universe, because while we understand fairly well how they form, understanding what happens at their edges, and especially what lies at their centers, pushes our theories to their breaking points. To understand that, we need to explore the event horizon in more detail, that invisible boundary where gravity becomes inescapable. The point of no return: understanding the event horizon. The event horizon is perhaps the most famous feature of a black hole, yet it's also one of the most misunderstood. It's tempting to think of it as a surface like the surface of a planet or the membrane of a balloon. But the event horizon is nothing like that. It's not made of anything. You couldn't touch it or bounce a ball off it. If you fell through it, you wouldn't feel yourself crossing it, at least not for a large black hole. The event horizon is a boundary in space-time itself, a demarcation that separates two regions with fundamentally different properties. The story of the event horizon begins with Karl Schwarzschild, a German physicist who was serving in the German army during the First World War in late 1915, just months after Einstein published his general theory of relativity. Schwarzschild found the first exact solution to Einstein's field equations. He was calculating the gravitational field around a spherical, non-rotating mass, and what he discovered was both mathematically elegant and physically strange. Schwarzschild's solution showed that for any mass, there exists a special radius, now called the Schwarzschild radius, where something remarkable happens. At this radius and beyond, the gravitational field becomes so strong that nothing, not even light, can escape. The formula for this radius is beautifully simple. It equals 2 times the gravitational constant times the mass, divided by the speed of light squared. For the Sun, despite its enormous mass of about 2 times 10 to the 30th kilograms, the Schwarzschild radius is only about 3 kilometers. Our Sun isn't anywhere near compact enough to be a black hole. Its actual radius is about 700,000 kilometers. But if you could somehow compress the Sun down to a sphere just 3 kilometers across, it would become a black hole. For Earth, the numbers are even more dramatic. Our planet's Schwarzschild radius is about 9 millimeters. Imagine compressing the entire Earth, all its mountains and oceans, its core of iron and mantle of rock, every living thing and every atom, into a sphere smaller than a marble. That's what it would take to turn Earth into a black hole. Let's think about what the event horizon actually means. The key is the concept of escape velocity, something we encounter in ordinary life, though we rarely think about it in those terms. If you throw a ball upward, it slows down as Earth's gravity pulls it back, eventually stopping and falling down again. Throw it faster, and it goes higher before falling. If you could throw it at about 11 kilometers per second, a speed called Earth's escape velocity, it would never fall back down. It would have enough energy to escape Earth's gravitational pull entirely. Every massive object has an escape velocity, and it depends on two things: the object's mass and your distance from its center. Get closer to a massive object, and the escape velocity increases. For most objects, you eventually hit the surface and can't get any closer. But imagine an object so compact that you could get close enough for the escape velocity to reach the speed of light. At that distance, light itself couldn't escape. That distance is the event horizon. The event horizon marks a boundary beyond which all future paths, all possible trajectories, lead inward toward the center. It's not that you need to travel faster than light to escape, it's that there is no direction you could travel, no path through space and time that leads outward. Inside the event horizon, outward ceases to exist as a direction you can move. Moving toward the center becomes as inevitable as moving forward in time. This creates one of the strangest effects in all of physics. Imagine you're watching someone fall toward a black hole. As they get closer to the event horizon, you notice something odd. They seem to be moving slower and slower. Their clock, which you can somehow see, ticks more and more slowly compared to your own. The light coming from them shifts redder and redder. They appear to freeze at the horizon, fading away but never quite crossing it. From your perspective, watching from a safe distance, they never actually enter the black hole. They just get closer and closer to the horizon, dimming and redding until they fade from view entirely. But from the perspective of the falling person, nothing special happens at the horizon. For a large black hole, the tidal forces at the horizon are actually quite gentle. They fall through the event horizon without noticing anything unusual. Their clock ticks normally from their point of view. They don't see themselves freezing or fading. They simply cross the boundary and continue falling inward. Only later, as they approach the center, do they begin to feel the tidal forces that will eventually tear them apart. This is one of the most mind-bending aspects of black holes. The falling observer's experience and the distant observer's perception are both valid, yet they seem completely contradictory. One sees an infinite approach, but never a crossing. The other experiences a straightforward fall through the horizon. Both perspectives are correct within their own reference frames. This isn't a failure of our observations or a trick of perception. It's a fundamental feature of how space-time works near a black hole. The event horizon is sometimes called the point of no return, but this phrase can be misleading. It suggests there's a moment when you cross a threshold and suddenly everything changes. The reality is subtler. The event horizon is defined not by what's happening at that boundary, but by what can happen in the future. A point is inside the event horizon if all possible future paths from that point lead to the singularity at the center. A point is outside if there exists at least one future path that leads to infinity. This means the event horizon is, in some sense, defined by the future. It's a teleological boundary, one determined by ultimate destinations rather than present conditions. This becomes even more apparent when you consider that the event horizon can grow. When matter falls into a black hole, the black hole's mass increases, and so does the size of its event horizon. In principle, you could be floating in empty space, apparently safe, when suddenly you find yourself inside an event horizon that just grew to encompass you, because someone threw enough matter into a black hole in your future. Real black holes in our universe come in different sizes. The smallest stellar black holes, formed from the collapse of massive stars, have masses of perhaps 5 to 10 times that of the Sun. Their event horizons are therefore about 15 to 30 kilometers in radius, not very large as cosmic objects go. You could drive that distance in your car in less than an hour if there were a road, but don't let the modest size fool you. The gravitational field near these small black holes is incredibly intense. Tidal forces would rip a human body apart long before reaching the horizon. At the other extreme are the supermassive black holes that lurk at the centers of most galaxies, including our own. Our galaxy's central black hole, Sagittarius A star, has a mass of about 4.3 million times that of the Sun. Its event horizon has a radius of about 12.7 million kilometers, larger than the orbit of Mercury around the Sun. And then there are the true monsters, like the black hole at the center of the M87 galaxy, which weighs about 6.5 billion solar masses. Its event horizon spans about 19 billion kilometers, more than 4 times the distance from the Sun to Neptune. These supermassive black holes are so large that the tidal forces at their event horizons are actually quite gentle. If you fell toward one, you could cross the event horizon without feeling anything unusual, at least initially. You'd have hours, possibly days of falling before the tidal forces became significant. This is counterintuitive. We tend to think bigger must mean stronger, but when it comes to tidal forces at the event horizon, bigger actually means gentler. The event horizon is often described as a one-way membrane. Things can go in, but can't come out. This is mostly true, but there's a subtlety worth noting. The event horizon isn't a physical barrier that stops things from coming out. Rather, from inside the horizon, the out direction doesn't exist. All future paths lead inward. It's like asking which direction is north from the North Pole. The question doesn't make sense because there is no north from that point. This one-way property means that black holes accumulate everything that crosses their horizons. Every atom that falls in adds to the black hole's mass. Every photon that crosses adds energy. Over time, as a black hole consumes nearby matter and merges with other black holes, it can grow to enormous sizes. The supermassive black holes at the centers of galaxies probably grew over billions of years, feeding on gas and stars and merging with other black holes during galactic collisions. But here's a question that puzzled physicists for decades. What happens to the information about matter that falls into a black hole? If you threw an encyclopedia into a black hole, would the information in that encyclopedia be lost forever? According to classical general relativity, yes. The matter crosses the horizon and is lost to the outside universe. Only the black hole's mass, charge, and spin change. All the other details, everything that makes the encyclopedia different from an equal mass of rocks or gas, vanishes behind the horizon. But quantum mechanics says information cannot be destroyed. This is a fundamental principle related to the unitarity of quantum evolution. If information were destroyed by black holes, it would represent a profound violation of quantum mechanics. This tension between general relativity and quantum mechanics is called the black hole information paradox, and it remains one of the deepest problems in theoretical physics. The event horizon stands at the center of this paradox. It's the boundary that separates us from the information that falls in. And it's also the location where quantum effects might modify the predictions of classical general relativity. Some physicists have suggested that the event horizon might not be as absolute as classical theory suggests. Stephen Hawking himself, late in his career, proposed that there might be no true event horizon, only an apparent horizon from which information could eventually escape. Others argue that the information is somehow encoded in subtle correlations in the Hawking radiation emitted by the black hole. We'll explore these quantum considerations more when we discuss Hawking radiation. For now, what's important is to understand that the event horizon, despite being empty space, despite having no physical structure, is one of the most important boundaries in the universe. It divides what can be observed from what cannot. It marks the point beyond which our most successful theory of gravity begins to encounter its limits, and it surrounds a region where space and time themselves behave in ways that challenge our deepest intuitions about the nature of reality. Before we venture deeper into the warped space-time near the singularity, take a moment to let this sink in. The event horizon is a boundary where the future becomes inevitable, where all paths lead to the same destination. It's a region where time and space exchange roles in a certain mathematical sense, where the coordinate that measures how far you are from the center becomes more like a time coordinate, ticking inevitably forward toward zero. It's a place that defines itself by what happens after you cross it, not by what exists at the crossing itself. And yet, for all its strangeness, the event horizon can be crossed. It's not a wall or a barrier, it's simply a point of no return. Once you understand that, you can begin to grasp what makes black holes so fascinating and so terrifying. They're not just objects with strong gravity, they're regions of space-time where gravity has become so strong that it has rewritten the rules of what's possible, where the future is no longer open, where destiny is absolute. Now, let's explore what creates this absoluteness. Let's look at how gravity warps space-time itself. The fabric torn: how gravity warps reality. To understand what happens near a black hole, we need to change how we think about gravity itself. For centuries, we thought of gravity as a force, something that reaches across space to pull objects together. Isaac Newton's law of gravity described this force beautifully, allowing us to predict the motions of planets and moons with remarkable accuracy. But Newton's theory, brilliant as it was, didn't explain what gravity actually is. It simply described what it does. Einstein changed everything with his general theory of relativity. In his vision, gravity isn't a force at all. Instead, mass and energy curve the geometry of space-time itself, and objects simply follow the straightest possible paths through this curved geometry. A planet orbiting a star isn't being pulled by a force. It's moving in a straight line through curved space-time, and that straight line happens to be an ellipse when viewed from our perspective. This sounds abstract, I know. Let's make it more concrete. Imagine space-time as a stretched rubber sheet. Now place a bowling ball on the sheet. The ball creates a depression, a well in the rubber. If you roll a marble near the bowling ball, the marble will curve toward it, spiraling down into the well. The marble isn't being pulled by a force emanating from the bowling ball. It's simply following the curvature of the sheet. This analogy has limitations. Real space-time is four-dimensional, not two-dimensional like a rubber sheet, and the curvature affects time as well as space, something the rubber sheet analogy can't capture, but it gives you a sense of the basic idea. Mass warps the geometry of space-time, and this warping is what we experience as gravity. Now imagine replacing the bowling ball with something much more compact. Squeeze the same mass into a smaller and smaller volume. The depression in the rubber sheet becomes deeper and steeper. The walls of the well become more vertical. Eventually, if you compress the mass enough, the walls become infinitely steep. The rubber sheet tears. This is what happens at a black hole. The curvature of space-time becomes so extreme that it essentially breaks the geometry. Near a black hole, this curvature affects everything. Time runs slower. Distances become distorted. Light follows curved paths, bending around the black hole in ways that can create multiple images of background objects. The closer you get to the black hole, the more extreme these effects become. And at the center, something truly bizarre happens. The curvature doesn't just become very large, it becomes infinite. This is the singularity, and it's where our understanding of physics breaks down completely. Let's approach this carefully, because the singularity is one of the most misunderstood concepts in black hole physics. First, we need to distinguish between different types of black holes. The simplest is the Schwarzschild black hole, which is non-rotating and has no electric charge. For this type of black hole, the singularity is predicted to be a single point at the center, a location where all the mass is concentrated into zero volume. Think about what this means. Zero volume means infinite density. All the mass that fell in to create the black hole compressed to a mathematical point. The curvature of space-time at this point is infinite. Time and space become so warped that the equations of general relativity simply stop working. They produce infinities, which in physics usually means you've pushed a theory beyond its domain of validity. Most physicists don't believe the singularity is literally a point of infinite density. Instead, they think the singularity represents the limit of general relativity, a signpost saying new physics needed here. What actually exists at the center of a black hole is one of the great unsolved questions in physics. Answering it requires a theory that combines general relativity with quantum mechanics, a theory of quantum gravity that we don't yet have. For rotating black holes, which are more realistic since most objects in the universe have at least some spin, the structure is different. These are called Kerr black holes, named after Roy Kerr, who discovered the solution in 1963. The rotation adds angular momentum, and this changes the geometry inside the event horizon. Instead of a point singularity, the mathematics predicts a ring singularity, a circle where the curvature becomes infinite. The ring singularity opens up strange possibilities. In principle, if you could avoid being destroyed by tidal forces, you might be able to pass through the ring without hitting the singularity. What would you encounter on the other side? The mathematical solutions suggest some extraordinary possibilities. Other universes, closed time-like curves, paths that loop back to their own past. But these mathematical possibilities almost certainly don't correspond to physical reality. The interior of a real black hole, with matter falling in and quantum effects at play, would be far more chaotic than these idealized mathematical solutions suggest. In the late 1960s, Soviet physicists Vladimir Belinsky, Isaac Kalatnikov, and Evgeny Lifshitz made an important discovery about what really happens near the singularity of a realistic black hole. They found that any perturbation, any matter or energy falling in, would cause the spacetime near the singularity to oscillate chaotically. The direction of stretching and squeezing would flip rapidly, creating what they called mixmaster dynamics, named after a popular kitchen mixer of the time. Imagine being caught in these oscillations. One moment you're being stretched vertically and compressed horizontally. A fraction of a second later, the directions reverse. Then they change again. The oscillations happen faster and faster as you approach the singularity, the tidal forces growing without limit, ripping apart anything unfortunate enough to be there. This is spaghettification, the informal term physicists use to describe being stretched into a long, thin strand by tidal forces. These tidal forces arise because gravity is stronger at points closer to the black hole. If you fell in feet first, your feet would be pulled more strongly than your head, stretching you vertically. At the same time, you'd be compressed horizontally as the gravitational field from all directions converges toward the center. For a small black hole, these forces would tear you apart long before you reached the event horizon. For a large black hole, you might survive crossing the horizon, but the tidal forces would eventually destroy you as you approached the singularity. Here's something that might surprise you. Inside the event horizon, the singularity isn't a place in space. It's a moment in time. Or rather, the coordinate that measures distance from the center acts more like a time coordinate once you're inside the horizon. Just as you inevitably move forward in time in the normal universe, once inside the horizon, you inevitably move toward the singularity. It's in your future, unavoidable, approaching with the inexorability of tomorrow. This is part of what makes black holes so profoundly strange. Outside the event horizon, you can stay at a fixed distance from the black hole by moving, by firing rockets, by exerting force inside the horizon. No amount of force can keep you at a fixed distance from the singularity. Moving toward it becomes as inevitable as aging. The singularity is not a place you can avoid going to. It's a time you cannot avoid reaching. Roger Penrose proved in 1965 that singularities are not just artifacts of simplified mathematical models. Under very general conditions, once an event horizon forms, a singularity must exist somewhere in the future of that horizon. This work, for which he received the Nobel Prize in Physics in 2020, showed that singularities are an inevitable consequence of gravitational collapse in general relativity, not just special cases that arise from assuming perfect symmetry. Penrose also proposed what he called cosmic censorship, the hypothesis that all singularities are hidden behind event horizons. The idea is that nature has a modesty principle. The breakdown of physics at a singularity is hidden from the rest of the universe by the event horizon. If naked singularities existed, singularities without event horizons, they could potentially affect the outside universe in unpredictable ways, breaking the determinism of physics. Most physicists hope cosmic censorship is true, though proving it rigorously has proven difficult. The extreme curvature near a black hole affects time in profound ways. The closer you get to the event horizon, the slower time passes relative to someone far away. This isn't an illusion or a matter of perception. It's a real difference in the flow of time, measured by real clocks. An astronaut hovering just above the event horizon of a large black hole could watch centuries pass in the outside universe in what feels to them like just a few hours. When they finally escaped back to safety, everyone they knew would be long dead. Entire civilizations might have risen and fallen. This time, dilation has been confirmed in much milder gravitational fields. Atomic clocks on satellites run slightly faster than clocks on Earth's surface, exactly as general relativity predicts GPS systems must account for this effect to maintain accurate positioning. Near a black hole, these effects are amplified enormously. Time doesn't just slow down, it approaches stopping altogether at the event horizon from the perspective of a distant observer. Light also behaves strangely near black holes. The curvature of spacetime bends the paths of light rays, an effect called gravitational lensing. If you could somehow observe from near a black hole, you would see bizarre distortions. Light from behind you could bend around the black hole and reach your eyes. Allowing you to see the back of your own head, stars would appear in wrong positions, their light bent by the warped space-time. If the black hole is rotating, it drags space-time around with it in an effect called frame dragging, causing additional distortions. At a certain distance from a black hole, at 1.5 times the Schwarzschild radius, there's a region called the photon sphere. Here, space-time is so curved that light can orbit the black hole. Photons traveling in just the right direction will circle the black hole, perhaps many times, before spiraling inward or escaping outward. If you were at the photon sphere and looked tangentially, you could see the back of your head, the light having completed a full orbit around the black hole. Closer still, at distances within about 5 times the Schwarzschild radius, stable orbits become impossible. Matter falling toward the black hole enters what's called the plunge region, accelerating rapidly inward. This is where much of the dramatic action around black holes occurs. Gas and matter spiraling inward form accretion disks. Friction heats the material to millions of degrees, and it radiates brilliantly in X-rays before crossing the event horizon. These accretion disks are how we detect most black holes. We can't see the black hole itself, but we can see the matter heating up as it falls in. All of this, the event horizon, the singularity, the warped spacetime, the time dilation, emerges from Einstein's equations of general relativity. These equations describe how matter and energy curve spacetime, and how this curvature affects the motion of matter and energy. Near black holes, these equations predict extreme effects, but they're the same equations that successfully describe GPS satellites and the orbit of Mercury and gravitational lensing around galaxies. Yet the equations also predict their own breakdown. The singularity, where curvature becomes infinite, is a place where general relativity stops making sense. The theory signals its own inadequacy. This isn't a failure of general relativity any more than Newton's gravity is a failure because it doesn't work near black holes. It's a theory reaching the boundary of its domain of validity. What lies at the center of a black hole, what replaces the infinite singularity when quantum effects are properly included, remains unknown. String theory, loop quantum gravity, and other approaches to quantum gravity all make different predictions. Some suggest the singularity is smoothed out into a region of finite but enormous curvature. Others propose that black holes might be fundamentally different objects than general relativity suggests. Some speculate about connections to other universes, or even to the creation of new universes. For now, these remain speculations. What we know for certain is that general relativity, one of our most successful theories, predicts its own breakdown at the centers of black holes. It's a profound statement about the limits of our current understanding. We have a theory that can describe the warping of spacetime around black holes with exquisite precision, that can predict the gravitational waves from black hole mergers detected billions of light years away. But that same theory tells us it cannot describe what happens at the very center. This is where we stand at the edge of knowledge. Black holes are real. We've detected them through their gravitational effects on surrounding matter. We've photographed their shadows against glowing accretion disks. We've measured the space-time ripples produced when they merge, but their interiors, hidden behind event horizons, wrapped around singularities where physics breaks down, remain beyond our current reach. Perhaps, though, black holes aren't quite as eternal and unchanging as classical general relativity suggests. Perhaps quantum mechanics has something to say about them after all, because in 1974, Stephen Hawking discovered something that surprised everyone, including himself. Black holes, he realized, are not entirely black. The slow whisper of decay, Hawking radiation. Stephen Hawking was 32 years old when he made the discovery that would define his career. He was already well known in physics circles for his work with Roger Penrose on singularities, and he was living with ALS, the disease that would gradually paralyze him over the following decades. In 1974, Hawking was thinking about how quantum mechanics might behave near the event horizon of a black hole, and his calculations led him to a conclusion so unexpected that he initially thought he'd made a mistake. Black holes, he realized, emit radiation. They glow ever so faintly with a thermal spectrum, and if they glow, they must lose energy. And if they lose energy, they must eventually evaporate. This was revolutionary. Black holes were supposed to be the ultimate one-way streets. Nothing escapes from beyond the event horizon. Nothing that was the whole point. Yet here was Hawking using rigorous quantum field theory calculations, showing that black holes must radiate. They must slowly and inexorably evaporate away. The popular explanation you've probably heard, goes something like this. Quantum mechanics allows particle-antiparticle pairs to spontaneously pop into existence from the vacuum for brief moments, borrowing energy from the uncertainty principle. Normally, these virtual particles quickly annihilate each other and disappear. But near a black hole's event horizon, one particle of the pair might fall into the black hole while the other escapes. The escaping particle becomes real, carrying energy away from the black hole, while the particle that fell in has negative energy, reducing the black hole's mass. This explanation is simple and memorable, but it's not quite accurate. It was an analogy Hawking himself used to popularize his discovery, but it's not what actually happens according to the mathematics. The truth is more subtle and more interesting. What Hawking actually calculated involves the concept of vacuum fluctuations in quantum field theory. Even empty space isn't truly empty in quantum mechanics. The vacuum is a seething sea of quantum fluctuations, fields oscillating at their zero-point energy, the lowest energy state allowed by the uncertainty principle. Normally, we don't notice these fluctuations. They average out. But near a black hole, spacetime is curved so dramatically that this changes things. Hawking performed a calculation comparing the quantum vacuum in curved spacetime near a black hole to the vacuum in flat spacetime far away. What he found was that what looks like empty vacuum in flat spacetime, when viewed from the perspective of curved spacetime near the black hole, actually contains particles. The intense curvature of spacetime itself creates real particles from the quantum vacuum. These particles can escape to infinity, carrying energy away from the black hole. The radiation has a thermal spectrum, meaning it looks exactly like the radiation from a hot object, with a temperature that depends inversely on the black hole's mass. The larger the black hole, the lower its temperature. A black hole with the mass of the Sun would have a temperature of about 1/10,000,000th of a degree above absolute zero. This is far colder than the cosmic microwave background radiation left over from the Big Bang, which is about 3 degrees above absolute zero, so a solar mass black hole would actually absorb more radiation than it emits, growing rather than shrinking. But smaller black holes are hotter. A black hole with the mass of the Moon would have a temperature of about 3 degrees Kelvin, similar to the cosmic microwave background, smaller still, and the temperature climbs. A black hole the mass of a large mountain might have a temperature of about room temperature, and very small black holes, if they exist, would be scorching hot. This inverse relationship between mass and temperature has a dramatic consequence. As a black hole radiates and loses mass, it gets hotter. As it gets hotter, it radiates faster. As it radiates faster, it loses mass more quickly, which makes it hotter still. The process accelerates runaway fashion until in the final moments the black hole explodes in a burst of high-energy radiation. Let's put some numbers to this. A black hole with the mass of our Sun would take about 10 to the power of 67 years to evaporate completely. That's far, far longer than the current age of the universe, which is only about 14 billion years, or about 10 to the power of 10 years. Even stellar mass black holes, the smallest ones we expect to form from collapsing stars, would take unimaginably long times to evaporate. Supermassive black holes take even longer. A black hole with a mass of 100 billion suns, like some of the largest black holes known, would take about 2 times 10 to the power of 100 years to evaporate. By comparison, the proton itself might decay on timescales of 10 to the power of 35 years or so. Though this hasn't been observed, the black holes would outlast ordinary matter by factors that dwarf comprehension. But the universe is patient. If nothing else interferes, if the universe keeps expanding and cooling, eventually even the largest black holes would evaporate. In the unimaginably distant future, after all stars have died and galaxies have dissipated and ordinary matter has decayed, the only remaining objects might be black holes, and then one by one, over timescales that make the current age of the universe seem like the blink of an eye, they would evaporate, leaving behind only the faint radiation of their passing. There's a caveat though. We've never actually detected Hawking radiation from a real black hole. The effect is too weak. The radiation from any astrophysical black hole is utterly dwarfed by other sources of radiation. We believe Hawking's calculation because it follows rigorously from quantum field theory in curved spacetime, and because it's consistent with other results in physics, but we haven't directly confirmed it through observation. However, there have been some remarkable laboratory experiments that support the basic physics. In 2010, researchers created what they called a sonic black hole using a flowing Bose-Einstein condensate, an exotic state of matter that exists at temperatures near absolute zero. In this system, the flowing atoms created an acoustic horizon for sound waves, analogous to the event horizon of a black hole for light. The researchers detected thermal radiation from this acoustic horizon, radiation that matched the predictions for Hawking radiation in the acoustic system. This doesn't prove that real black holes emit Hawking radiation, but it shows that the underlying physics, the creation of thermal radiation from horizons, is sound. It's as close as we're likely to get to experimental confirmation until we develop much more sensitive instruments, or until we discover primordial black holes small enough to be radiating significantly. Primordial black holes are a hypothetical type of black hole that might have formed in the very early universe, not from stellar collapse but from density fluctuations in the primordial plasma. If they exist, some of them could be much smaller than stellar mass black holes. Hawking calculated that any primordial black hole with a mass less than about 10 to the power of 12 kilograms, roughly the mass of a large asteroid, would have evaporated completely by now. So if small primordial black holes existed, we might expect to see the final bursts of Hawking radiation as they explode. None have been detected yet, which either means they don't exist or they're too rare to have been observed in our vicinity. The discovery of Hawking radiation raises profound questions about information and entropy. According to the calculations, the radiation is purely thermal. It has a temperature but no other distinguishing features. This means that if you watched a black hole evaporate completely, all you would see at the end is thermal radiation, radiation that carries no information about what fell into the black hole to form it. Whether the black hole was made from stars or encyclopedias or computers, the final radiation would be the same. But quantum mechanics insists that information cannot be destroyed. If you have complete information about a quantum system at one time, the laws of quantum mechanics allow you to calculate its state at any other time, forward or backward. This is called unitarity, and it's a fundamental principle. If black hole evaporation destroys information, it would violate unitarity, breaking one of the foundations of quantum mechanics. This is the black hole information paradox, one of the deepest problems in theoretical physics. Hawking himself initially argued that information was lost, that black holes provided an exception to the usual rules of quantum mechanics, but most physicists found this troubling. Over decades, many proposals have been made to resolve the paradox. Perhaps information is encoded in subtle correlations in the Hawking radiation in ways that aren't apparent from the thermal spectrum. Perhaps information escapes through other channels. Perhaps the interior and exterior of the black hole are connected in unexpected ways that preserve information. Recent work, particularly using ideas from string theory and quantum gravity, suggests that information probably is preserved, though the details of how remain contentious. Some physicists propose that information is encoded on the event horizon itself in a holographic fashion, with the three-dimensional information of the interior somehow represented in a two-dimensional form on the boundary. Others propose that the final moments of evaporation, when the black hole reaches near Planck scale sizes, involve physics so different from what we currently understand that information can escape then. There's also a remarkable development from 2023 that's worth noting. Physicists Michael Wondrak, Walter van Zuylichem, and Heino Falke published calculations showing that Hawking radiation might not require an event horizon at all. They demonstrated that the curvature of space-time alone, even far from any horizon, can create particle pairs through quantum effects. Based on these theoretical calculations, any massive object, not just black holes, might produce a Hawking-like radiation, though the effect would be exponentially weaker for objects without horizons. If this theoretical framework is correct, it would mean everything in the universe is very, very slowly evaporating. Stars, planets, even you, would be emitting faint quantum radiation due to the curvature of space-time around your mass. The timescales are absurd, far exceeding even the evaporation time of supermassive black holes, but the principle would be the same. In the unimaginably distant future, not only would black holes evaporate, but potentially every other massive object as well. This paints a hypothetical picture of one possible fate of the universe that's both bleak and strangely beautiful. In such a far future scenario, long after the last star has died, long after even black holes have evaporated, the universe might consist of nothing but a thin, cooling gas of radiation spreading ever more thinly as space continues to expand. The structures we see now, galaxies and stars and planets and life, would be a brief efflorescence in the early universe, a moment of complexity before the long, slow slide toward maximum entropy. But this is speculation layered upon speculation. We don't know if the universe will expand forever or eventually contract. We don't know if protons decay or remain stable. We don't know what dark energy is or what it will do in the far future. And we certainly don't have a complete theory of quantum gravity that could definitively answer these questions. What Hawking radiation does tell us, though, is that black holes are not the eternal, unchanging objects they appear to be in classical general relativity. They're dynamic, evolving, subject to quantum effects. They emit radiation, they lose mass, and given enough time, they disappear. The timescales are so long that no black hole in our current universe will evaporate before the universe is many, many times its current age. But the principle is established. Nothing is truly eternal. Even black holes, the most extreme objects we know of, eventually yield to the patient, relentless processes of quantum mechanics. And that brings us to even more speculative territory. If black holes can form and evaporate, if they warp spacetime into impossible geometries, what other exotic structures might the universe contain? What about wormholes, tunnels connecting distant parts of spacetime? What about white holes, the time-reversed twins of black holes? Let's venture carefully into these theoretical possibilities, keeping in mind that we're now at the very edge of established physics, looking out into realms where mathematics suggests possibilities, but nature may have other ideas. Beyond the edge of known wormholes. In 1935, just months after Carl Schwarzschild discovered the solution describing a black hole, Albert Einstein and his colleague Nathan Rosen were exploring that solution more carefully. They discovered something unexpected hidden in the mathematics. The equations seemed to describe not just one region of space, but two, connected by a kind of bridge. This bridge, now called an Einstein-Rosen bridge or simply a wormhole, appeared to be a tunnel through space-time connecting two different locations. Imagine folding a piece of paper so that two distant points touch. Now imagine poking a hole through both layers at once, creating a tunnel connecting the 2 points. That tunnel is analogous to a wormhole, a shortcut through space-time that might allow you to travel between distant locations without traversing the space in between. It's an idea that sounds like science fiction, but it emerges from the same equations that successfully describe gravity throughout the universe. There's just one problem. The Schwarzschild wormhole, the one Einstein and Rosen discovered, doesn't work as a shortcut. It's not traversable. Let me explain what this means. When mathematicians and physicists solve Einstein's equations, they often find solutions that describe eternal idealized objects that have existed forever and will exist forever. The Schwarzschild solution, in its maximally extended form, describes an eternal black hole that never formed from collapsing matter. If you draw a diagram of the full space-time structure, you find not just a black hole region in the future, but also a white hole region in the past, and two separate external regions that could be thought of as two different universes. The wormhole is the connection between these two external regions. But here's the catch. This connection exists only for an instant. If you tried to travel through the wormhole from one external region to the other, you'd have to move faster than light. The wormhole's throat, the narrow connection between the two mouths, pinches off too quickly. Before any signal or particle can traverse it, it collapses, severing the connection. John Archibald Wheeler and Robert Fuller proved this mathematically in 1962. They showed that the Einstein-Rosen bridge is inherently unstable. Any particle trying to pass through would arrive at the throat just as it closed. The two external regions remain forever causally disconnected. The wormhole is there in the mathematics, but it's not useful for communication or travel. This might seem like the end of the story for wormholes, but physicists have explored a potential theoretical loophole, though it requires something quite exotic. In the 1980s, Kip Thorne and his colleagues investigated whether you could hold a wormhole open using what's called exotic matter, matter with negative energy density. In ordinary physics, energy is positive. An object at rest has mass energy. A moving object has additional kinetic energy. Radiation carries positive energy, but quantum field theory allows, under certain circumstances, for regions of space to have negative energy density relative to the vacuum. This doesn't mean negative mass in the usual sense, but rather energy density less than the zero-point energy of empty space. Thorne's theoretical calculations showed that if you could somehow line the throat of a wormhole with exotic matter, you might be able to hold it open, preventing it from collapsing. The exotic matter would have negative energy density, and its gravitational effect would be repulsive rather than attractive, propping the throat open against its tendency to pinch off. How much exotic matter would you need? The amounts are fantastically large, and it's not clear whether exotic matter can be produced or concentrated in sufficient quantities. Some quantum effects, like the Casimir effect, do produce negative energy densities on small scales, but scaling these up to hold open a macroscopic wormhole may not be possible. The laws of physics impose severe restrictions on negative energy, preventing it from being too concentrated or lasting too long. Moreover, even if you could hold a wormhole open, creating one in the first place poses another enormous challenge. You'd essentially need to create a controlled, highly curved region of spacetime with a very specific topology. In theory, you might be able to do this if you could manipulate quantum fluctuations at the Planck scale, or if you had access to cosmic strings or other exotic structures from the early universe. But these are all speculative possibilities, far beyond anything we can currently achieve or even imagine achieving. There's a more recent theoretical development worth mentioning. In 2021, physicists proposed that microscopic wormholes might be possible without requiring exotic matter, if they're supported instead by charged fermionic matter, particles like electrons. The key is that the particles must have small enough mass that they can't collapse into a charged black hole. These wormholes, if they could exist, would be incredibly small, probably too small to allow anything larger than subatomic particles through, and they might only permit information transfer rather than matter transport. But the theoretical work suggests that the requirement for exotic matter might not be as absolute as once thought. String theory, a candidate for a theory of quantum gravity, suggests other theoretical possibilities. In some versions of string theory, especially those involving extraspatial dimensions, wormhole-like structures might exist naturally. Brains, higher dimensional objects in string theory, might be connected in ways that resemble wormholes. The Randall-Sundrum models, which describe our universe as a four-dimensional brain embedded in a higher dimensional space, theoretically allow for the possibility of traversable wormholes without exotic matter. However, these models remain highly speculative and have not been confirmed by observation. Even if stable, traversable wormholes could theoretically exist, there's another problem: time travel. If a wormhole connects two distant locations in space, you might be able to convert it into a time machine, by accelerating one mouth of the wormhole relative to the other, using time dilation effects to create a time difference between the mouths. You could then travel through the wormhole from one era to another. This raises all the familiar paradoxes of time travel. Could you go back in time and prevent yourself from entering the wormhole in the first place? Some physicists, including Hawking, have argued that nature must have some chronology protection mechanism that prevents time machines from forming. Perhaps quantum effects would cause the wormhole to collapse just as it was about to become a time machine. Perhaps the buildup of vacuum fluctuations would destroy it. The theoretical mathematics remains unclear, and physicists continue to debate whether time travel is truly forbidden by the laws of physics or merely extremely difficult. What about wormholes connecting to other universes rather than different parts of our own universe? This idea appears in the mathematics of eternal black holes. The maximally extended Schwarzschild solution has two external regions that could be interpreted as two different universes. The black hole interior contains matter that fell in from either universe, and the white hole interior emits matter into either universe. But this is an idealized eternal solution. Real black holes form from gravitational collapse, and this removes the white hole and the second external universe from the picture. What's left is just our universe, with a black hole in it, and no connection to anywhere else. Some cosmological models do propose connections between different universe-like regions through wormholes. Eternal inflation, a theory about the very early universe, suggests that space is continuously creating new inflating regions, bubbles that could be thought of as separate universes. Perhaps these models suggest wormholes might connect these regions. Perhaps the Big Bang itself emerged from a white hole that was the exit of a black hole in another universe. These ideas are mathematically consistent, but remain purely speculative, with no observational evidence to support them and considerable debate about whether they're even testable in principle. Could we ever detect a wormhole if one existed? Perhaps. If a wormhole mouth was in our vicinity, we might be able to detect it through gravitational lensing effects as light from background objects bent around it. A wormhole mouth would look similar to a black hole from a distance, but with some differences. Matter could emerge from a wormhole, whereas nothing emerges from a black hole. A wormhole might have different accretion disk properties. Some physicists have suggested that if black holes could fall into wormholes, we might detect the resulting gravitational wave signals, which would differ from black hole merger signals. But so far, no such signals have been detected. Gravitational wave observatories like LIGO and Virgo have detected dozens of black hole mergers, and the signals all match the predictions for black holes colliding and merging, not for black holes encountering wormholes or other exotic objects. This doesn't prove that wormholes don't exist, but it suggests they're not common, at least not in forms that would produce detectable signals. The honest assessment is this: wormholes are allowed by the equations of general relativity under certain conditions, but we have no evidence they actually exist. Creating a traversable wormhole would require exotic matter or other conditions that may not be achievable in practice. Even if they could exist, they might be microscopic or unstable, or unable to transport macroscopic objects. They remain, for now, mathematical curiosities and staples of science fiction rather than confirmed physical objects. Yet they're not impossible. The universe has surprised us before. Black holes themselves were once considered too strange to be real, mathematical artifacts that surely couldn't exist in nature, but they do exist. We've seen them now, photographed their shadows, measured their gravitational waves. Perhaps wormholes will follow a similar path from speculation to observation, or perhaps they'll remain forever in the realm of theoretical possibility, tantalizing hints in the equations that nature chooses not to realize. And speaking of mathematical possibilities that might or might not be real, let's turn to another idea that emerges from Einstein's equations. White holes, the time-reversed twins of black holes, objects that would be even stranger than wormholes if they exist at all. The time-reversed twin, white holes. If black holes are regions where nothing can escape, white holes are their opposites, regions where nothing can enter. If a black hole is a cosmic drain pulling everything into itself, a white hole would be a cosmic fountain, spewing matter and energy outward, but allowing nothing to fall in. It sounds absurd, but like wormholes, white holes appear in the mathematical solutions to Einstein's equations. The question is whether they correspond to anything real. The concept of a white hole emerges from the time reversal symmetry of Einstein's equations. General relativity describes how space-time curves in response to matter and energy. But the equations themselves don't distinguish between past and future in any fundamental way. They're time-symmetric. If you have a solution describing matter collapsing into a black hole, you can run time backward and you get a solution describing matter exploding out of a white hole. This time-reversed solution is mathematically valid. It satisfies Einstein's equations just as well as the forward time version, but mathematical validity doesn't guarantee physical realizability. Just because an equation has a solution doesn't mean that solution describes something that actually exists or can be created. Think about the maximally extended Schwarzschild solution we discussed when talking about wormholes. That solution contains both a black hole region in the future and a white hole region in the past. The white hole is where the wormhole bridge connects to, or rather where it emerged from, in the distant past. But remember, this is an eternal solution, describing an object that has always existed and will always exist. Real black holes form from gravitational collapse, and when you include that formation process in the mathematics, the white hole region disappears. It's an artifact of the eternal idealized solution, not something that appears in realistic scenarios. So can white holes form in our universe? Most physicists think not, at least not through any process we currently understand. The problem is thermodynamics, specifically the second law of thermodynamics, which says that entropy, a measure of disorder, always increases over time in a closed system. A white hole would appear to violate this. Imagine a white hole spewing out matter and energy in a coordinated, organized fashion. That matter was previously in a highly compressed, high-entropy state inside the white hole, but it emerges as distinct particles and radiation that could potentially form stars or planets or other low-entropy structures. It resembles watching a video of an explosion run backward, with debris flying together to form an intact object. It's time-reversed but thermodynamically problematic. Moreover, based on theoretical analysis, white holes would be incredibly unstable. Even if one formed somehow, any matter in its vicinity would fall toward it due to gravity. But a white hole, by definition, doesn't allow things to enter. What happens when an irresistible force meets an immovable object? In this case, the mathematics suggests that matter accumulating outside the white hole's event horizon would cause the white hole to collapse and convert into a black hole almost immediately. Despite these problems, some physicists have explored whether white holes might exist in certain contexts. One intriguing possibility comes from loop quantum gravity, a candidate theory for quantum gravity that treats space-time as composed of discrete quantum building blocks rather than a smooth continuum. In loop quantum gravity, the extreme conditions at a black hole's singularity are modified by quantum effects. The theory proposes that space-time can't be compressed to infinite density. There's a quantum bounce, a limit to how small and dense regions can become. Hal Haggard and Carlo Rovelli, physicists working on loop quantum gravity, have proposed a theoretical scenario in which black holes might not end in singularities at all. Instead, they might undergo a quantum transition, bouncing from a black hole to a white hole. Here's how their proposal works. Matter collapses into a black hole, compressing toward the center. But instead of forming a singularity with infinite density, quantum gravitational effects halt the collapse at some finite, albeit extremely high, density. The matter then rebounds, transforming the black hole into a white hole that explodes outward. This transition might take only a few thousandths of a second from the perspective of someone inside the black hole. But because of time dilation effects, from the perspective of an outside observer, the transition could take an extraordinarily long time. Based on this theoretical framework, small black holes that formed in the very early universe might be reaching the end of their black hole phase now, billions of years later, and transitioning to white holes. These white holes would then explode, releasing their accumulated mass energy in a burst of radiation. Haggard and Rovelli have suggested that some gamma-ray bursts, powerful explosions we observe in the distant universe, might actually be white hole explosions from primordial black holes. This is an exciting idea, but it's highly speculative. We'd need more observational evidence to support it, and we'd need a more complete theory of quantum gravity to make firm predictions. Other quantum gravity approaches don't necessarily predict black-to-white transitions. String theory, for instance, suggests different possibilities for what happens at the cores of black holes. There's also the question of whether white holes could be connected to black holes through wormholes, as the Schwarzschild solution suggests. In this picture, matter falling into a black hole might travel through a wormhole and emerge from a white hole in a different location or even a different universe. But as we discussed, the wormhole connection in realistic scenarios is either absent or untraversable, so this probably doesn't happen. Another highly speculative idea connects white holes to the Big Bang. Our universe began in a state of extremely high density and temperature, then expanded rapidly. In some ways, this resembles what you'd expect from a white hole, a massive outpouring of matter and energy from a compact region. Could the Big Bang have been a white hole? Some cosmological models have explored this idea, suggesting that our universe might have emerged from a black hole in a parent universe. These models are fascinating but extremely difficult to test. If our universe is the interior of a white hole connected to a black hole in another universe, we'd have no way to observe that other universe or verify the connection. We can only work with observations made from within our universe, and those observations are generally consistent with standard Big Bang cosmology without requiring the white hole hypothesis. The mainstream view among physicists is that white holes probably don't exist in our universe, at least not as stable, long-lasting objects. They might appear transiently in the quantum gravitational dynamics of black holes, or they might be forbidden entirely by thermodynamic or quantum effects. The mathematics allows them, but mathematics allows many things that nature doesn't realize. Yet the theoretical possibility remains tantalizing. If loop quantum gravity is correct, and if black holes do transition to white holes after long periods, we might eventually observe the signals. Future gravitational wave detectors might pick up the characteristic signatures of these transitions. High-energy telescopes might identify unusual gamma-ray bursts that don't quite match supernova or merger models, and theoretical work continues, exploring the conditions under which white holes might form and what their observable properties would be. For now, white holes remain on the speculative edge of physics, more mathematical curiosity than confirmed reality. They remind us that our understanding of extreme gravity is still incomplete, that quantum effects at the Planck scale might modify the predictions of classical general relativity in unexpected ways. And they hint that the universe might be even stranger and more varied than we currently know. This brings us to a crucial point about everything we've discussed in the last two sections. Wormholes, white holes, the detailed structure of singularities, even the ultimate fate of black holes through Hawking radiation. All of these involve physics at the boundaries of our current understanding. They require reconciling general relativity with quantum mechanics, two theories that have both been extraordinarily successful in their domains, but that don't yet fit together into a unified framework. Let's step back now and consider what we don't know, the questions that remain open, the frontiers where our physics breaks down and new theories are needed. The edge of understanding, what we don't know. We've journeyed deep into the realm of black holes, exploring their formation, their event horizons, the warping of space-time around them, the slow evaporation through Hawking radiation, and the speculative possibilities of wormholes and white holes. But perhaps the most honest thing I can tell you is how much we don't know. How many questions remain unanswered? How many mysteries lie hidden behind the veil of the event horizon and in the quantum foam at the Planck scale? General relativity has been one of the most successful theories in the history of physics. Its predictions have been confirmed again and again, from the bending of starlight by the sun to the gravitational redshift of light to the existence of gravitational waves. When Einstein first proposed the theory in 1915, many of its predictions seemed too strange to be true. Black holes predicted by the mathematics were dismissed by Einstein himself as mathematical artifacts that couldn't really exist. Gravitational waves were controversial for decades, but observation after observation has vindicated the theory. Yet general relativity is incomplete. It can't be the final word on gravity because it breaks down at singularities. When the equations produce infinities, that's a signal that the theory has been pushed beyond its domain of applicability. It's like using Newtonian physics to describe objects moving near the speed of light. Newton's laws work beautifully for everyday speeds, but they break down at relativistic velocities, and you need special relativity to get the right answers. Similarly, general relativity works beautifully for describing space-time curvature at accessible scales, but it breaks down at the extreme densities and curvatures found at black hole singularities. What's needed is a theory of quantum gravity, a framework that combines general relativity's description of curved spacetime with quantum mechanics' description of the microscopic world. This has been one of the greatest challenges in theoretical physics for more than half a century. The problem is that gravity is different from the other forces of nature. The electromagnetic force, the weak nuclear force, the strong nuclear force, all have been successfully described using quantum field theories. But gravity resists this treatment. The reason has to do with the nature of spacetime itself. In quantum field theories of other forces, spacetime is treated as a fixed background, a stage on which quantum fields perform. But in general relativity, spacetime itself is dynamic, curved by matter and energy. Quantum gravity requires treating spacetime itself as quantum mechanical, with all the attendant uncertainties and fluctuations. At the Planck scale, distances of about 10 to the negative 35 meters and times of about 10 to the negative 43 seconds, quantum fluctuations of spacetime become significant. Space and time themselves become uncertain, fluctuating. Our familiar notions of smooth, continuous spacetime break down. Several approaches to quantum gravity have been developed, each with different assumptions and predictions. String theory proposes that fundamental particles are not point-like, but are instead tiny, vibrating strings. The different vibration modes of these strings correspond to different particles. In string theory, gravity emerges naturally from the vibrations of closed loops of string. The theory requires extra spatial dimensions beyond the three we experience, dimensions that are curled up at scales too small for us to detect directly. String theory has had some success in describing certain aspects of black holes. It can calculate black hole entropy, the amount of disorder encoded in a black hole, and get answers that match Hawking's results from general relativity. Some versions of string theory, particularly the fuzzball models, suggest that black holes don't have singularities at all. Instead, the black hole's interior is filled with a complex quantum structure, strings and branes in elaborate configurations. The event horizon in this picture is not a sharp boundary, but a fuzzy region where the quantum structure becomes too complex to describe classically. Loop quantum gravity takes a different approach. Instead of starting with strings in extra dimensions, it quantizes spacetime itself, treating it as woven from discrete loops at the Planck scale. Space, in this view, is not continuous but granular, made up of discrete quanta. Loop quantum gravity predicts that the singularities at black hole centers are avoided. The collapse halts at Planck scale densities and rebounds, potentially leading to the white hole transitions we discussed earlier. Other approaches exist as well. Causal set theory treats spacetime as a discrete set of points with causal relationships between them. Asymptotic safety is a framework suggesting that quantum corrections to gravity might make the theory well-behaved, even at high energies. Emergent gravity theories propose that spacetime and gravity are not fundamental, but emerge from more basic quantum information. None of these approaches is complete or confirmed. We don't have experimental evidence that decisively supports one theory over the others. This is partly because quantum gravitational effects are most important at energy scales and length scales, far beyond what we can probe with current technology. Particle accelerators like the Large Hadron Collider reach energies of about 10 trillion electron volts, enormous by everyday standards, but still 17 orders of magnitude below the Planck energy, where quantum gravitational effects become dominant. Still, black holes offer one of the few contexts where quantum gravitational effects might be observable, at least in principle. The information paradox, the question of what happens to information that falls into a black hole, touches directly on the interplay between quantum mechanics and gravity. Resolving this paradox will likely require insights from quantum gravity. Recent work has suggested that information is preserved, encoded in the Hawking radiation in subtle ways. The key insight involves quantum entanglement between the interior and exterior of the black hole particles created near the horizon are entangled with the black hole's interior in such a way that the radiation carries information about what fell in. The details are complex and involve sophisticated concepts from quantum information theory, but the upshot is that unitarity, the principle that information is conserved in quantum mechanics, is probably preserved even for black holes. But many questions remain. What exactly is the interior of a black hole like? Is there really a singularity, or does quantum gravity smooth it out into a region of extreme but finite curvature? Can observers ever access information from inside a black hole's event horizon, or is it forever hidden? If black holes eventually evaporate completely through Hawking radiation, what happens in the final moments when the black hole reaches Planck-scale size? Does it disappear in a final burst of radiation, or does something else happen? And what about naked singularities? Singularities not hidden behind event horizons. Penrose's cosmic censorship hypothesis suggests these shouldn't exist, that all singularities are decently clothed by horizons, but proving this rigorously has been difficult. Some solutions to Einstein's equations do appear to allow naked singularities under certain contrived conditions. Would quantum effects prevent their formation, or might they actually exist in some form? Gravitational wave astronomy, inaugurated by LIGO's detection of colliding black holes in 2015, offers new ways to study black holes. The waves carry information about the masses, spins, and dynamics of the merging objects. Future detectors, like the proposed Cosmic Explorer and Einstein telescope, will be much more sensitive, potentially detecting signals from black holes across the observable universe. These observations might reveal unexpected features, deviations from general relativity's predictions, hints of quantum gravitational effects. There's also the possibility of detecting primordial black holes if they exist. These would be relics from the very early universe, formed not from stellar collapse, but from density fluctuations in the first fraction of a second after the Big Bang. They could range from microscopic to millions of solar masses. If primordial black holes exist in sufficient numbers, they might account for some or all of the mysterious dark matter that makes up about 85% of the matter in the universe. Detecting them through gravitational lensing or gravitational waves or their evaporation products would be a major discovery. We also don't fully understand the relationship between black holes and thermodynamics. Black holes have entropy, a well-defined temperature, and they obey laws analogous to the laws of thermodynamics. This hints at deep connections between gravity, quantum mechanics, and information theory. Some physicists think that spacetime itself might emerge from quantum entanglement, that the smooth geometry we observe is a collective phenomenon arising from countless quantum links. The holographic principle, inspired by black hole thermodynamics, suggests that all the information in a volume of space can be encoded on the boundary of that region, like a hologram encodes three-dimensional information on a two-dimensional surface. This principle has led to profound insights in string theory and has changed how physicists think about the nature of space and reality. And then there are the philosophical questions. What does it mean that we can't observe inside a black hole's event horizon? Does the unobservable interior even exist in any meaningful sense? Or is the horizon the fundamental reality? If information is preserved in black hole evaporation, as quantum mechanics requires, where is it during the lifetime of the black hole? These questions touch on the nature of reality, observation, and the limits of knowledge. The honest answer is that we're still working on these problems. We've made remarkable progress. We understand black holes far better than we did 50 years ago, but many of the deepest questions remain open. We stand at the boundary of known physics, peering into a realm where our current theories fade into speculation and where new principles, perhaps radically different from anything we've encountered before, may be needed. This isn't a failure. It's the frontier of science, the edge where the known meets the unknown. And it's beautiful in its way to stand at that edge and acknowledge the vastness of what remains to be discovered. Black holes, these extreme objects where gravity becomes absolute, serve as laboratories for testing our most fundamental theories. They push our understanding to its limits and beyond, pointing the way toward new physics that might finally unite quantum mechanics and general relativity into a coherent whole. For now, though, the mysteries remain. The singularities hidden behind horizons keep their secrets. The quantum structure of space-time at the Planck scale remains beyond our reach, and the ultimate fate of black holes and of the universe itself lies shrouded in uncertainty and possibility. Let's bring our journey to a close, stepping back from these cosmic extremes to reflect on what they mean for our understanding of the universe and our place within it. Living with mystery. We've travelled far tonight, you and I, from the violent births of black holes in the collapse of massive stars to the invisible boundary of the event horizon where time and space exchange their meanings. We've explored how gravity warps space-time into impossible geometries, how singularities challenge our understanding of reality itself, how quantum mechanics predicts that even black holes must eventually evaporate. We've ventured into speculation about wormholes and white holes, and we've acknowledged the vast territories of the unknown, where our current physics gives way to questions we can't yet answer. It's a lot to contemplate. These objects, black holes, represent some of the most extreme conditions in the universe. They're places where density and curvature become so large that our everyday intuitions fail completely, where the distinction between past and future becomes absolute, where the flow of time itself can grind towards stillness, where space can be torn and twisted into topologies that seem impossible and yet they're real. They exist in our universe. They're not just mathematical curiosities, but physical objects that we can observe indirectly through their effects on matter and light, and directly through the gravitational waves they produce when they collide. What does it mean that such things exist? On one level, it's a testament to the power of human understanding. We've never been to a black hole, we never will. The nearest known black hole is still hundreds of light years away, and even if we could travel there, approaching too close would be fatal. Yet through mathematics, through physics, through the interplay of theory and observation, we've learned to understand these objects. We've measured their masses and spins. We've photographed the shadow of a supermassive black hole silhouetted against glowing gas. We've detected the ripples in space-time produced when they merge. This is an extraordinary achievement of collective human effort spanning more than a century. But it's also humbling, because for all we've learned, the deepest secrets remain hidden. We can describe the exterior of a black hole with exquisite precision. We can predict how matter behaves as it approaches the horizon. We can calculate the temperature and spectrum of Hawking radiation, but we cannot observe the interior. We cannot resolve the singularity at the center. We cannot definitively answer whether information is truly preserved or what happens in the final moments of evaporation. We stand at the event horizon, that boundary between the known and the unknowable, and we can go no further. There's something appropriate about this. Black holes are, in a sense, the universe's way of saying this far and no further. They represent the limits of observation, the limits of causality, perhaps even the limits of knowability. They remind us that the universe is under no obligation to make itself fully transparent to our understanding. Some things may be forever beyond our reach, not because we lack the cleverness or technology to access them, but because the structure of reality itself forbids it. And yet, paradoxically, this limit drives us to deeper understanding. The black hole information paradox has inspired decades of research into quantum gravity, leading to insights that might never have been found if black holes simply behaved according to classical physics. The existence of event horizons has forced us to think carefully about the nature of time, causality, and observation. The singularities have pointed the way toward the need for new physics, new principles that might finally unite the quantum and the gravitational. In a way, black holes are teachers. They show us where our theories break down. They reveal inconsistencies between frameworks that both seem correct in their domains. They challenge us to think more deeply, to find new ways of understanding reality that can encompass both the smoothly curved spacetime of general relativity and the granular probabilistic world of quantum mechanics. Consider how far we've come. A century ago, general relativity was brand new and untested. Black holes were mathematical oddities in Schwarzschild's solution, dismissed by Einstein himself. Today, we have images of black holes. We detect their gravitational waves routinely. We use them to test fundamental physics. The journey from speculation to observation took a century of theoretical development and technological advance. But it happened. We went from not knowing if black holes could exist to having detailed observations of them. What might we learn in the next century? Will we develop a complete theory of quantum gravity, one that can describe the interior of black holes without singularities? Will we find evidence of Hawking radiation, perhaps from primordial black holes or through increasingly sensitive experiments? Will we discover that the universe is stranger still, with wormholes or white holes or entirely unexpected phenomena? Or will we find that some mysteries remain forever beyond our grasp, protected by the event horizons that separate us from the answers? We don't know. And that's okay. Living with mystery, with uncertainty, with the vast expanse of the unknown, is part of what it means to engage with the universe. Honestly, science is not about certainty. It's about carefully building knowledge, testing ideas against observation, acknowledging what we don't know, and continuing to explore black holes, extreme and bizarre as they are part of our universe. They're part of the cosmos we inhabit. And understanding them, even partially, even imperfectly, enriches our sense of what reality is and what it can be. There's something almost peaceful in contemplating black holes, despite their violent origins and extreme nature. They follow laws, just like everything else. Those laws may be strange to us, may challenge our intuitions, but they're laws nonetheless. A black hole doesn't act capriciously. It doesn't violate the principles of physics. It's an extreme manifestation of those principles, a limiting case. But it's lawful, predictable in its way. If you know its mass, charge, and spin, you know how it will behave. There's an elegant simplicity to that. And in the far future, long after the last stars have died, when the universe is dark and cold, black holes will be the last remaining structures. They'll persist for unimaginable timescales, slowly radiating away their mass through Hawking radiation, gradually evaporating. And then eventually, they'll be gone, leaving behind only faint whispers of radiation spreading through the expanding void. This is both bleak and beautiful. The universe has a lifetime. Structures have lifetimes. Even black holes are temporary. Nothing is truly eternal. Everything changes, everything evolves, everything eventually fades. But while they last, black holes are magnificent, terrible, awe-inspiring testament to what gravity can do when it's given full reign. We live in a universe that contains black holes. That simple fact tells us something profound about the nature of reality. It tells us that gravity is not just a force that keeps our feet on the ground or holds the Earth in orbit around the Sun. Gravity is the curvature of space-time itself, and that curvature can become so extreme that it tears the fabric of reality, creating regions from which not even light can escape. It tells us that the universe is far stranger, far more extreme, far more varied than our everyday experience would suggest. You might never think about black holes in your daily life. They're too distant, too exotic, too removed from everyday concerns, and that's fine. But knowing they exist, knowing something about how they work, knowing what they reveal about the structure of space-time and the limits of our knowledge, that adds a dimension to your understanding of the cosmos. It places our small corner of the universe with its stable stars and habitable planets in context. We live in a relatively gentle region of space-time, where curvature is mild and gravity is weak. But the universe also contains places where gravity is anything but gentle, where it becomes absolute, dominant, the only force that matters. As you drift off to sleep tonight, perhaps you'll carry with you some sense of these distant, extreme objects. Black holes, where gravity becomes absolute, where space and time are warped beyond recognition, where the event horizon marks a boundary that can be crossed but never recrossed, where singularities hide, shielded from our view, keeping their secrets, where quantum mechanics whispers that nothing is truly eternal, that even these cosmic monsters must eventually fade. They're out there, in the darkness, scattered across the universe, strange and terrible and beautiful. Reminders that the cosmos is vast and full of wonders, that our understanding, vast as it is, remains incomplete, and that mystery and awe are part of the universe's gift to those who contemplate it. Rest now. Let these vast ideas settle into your mind like sediment drifting to the bottom of a still pond. The black holes will continue their ancient dance through the cosmos, pulling in matter, warping space-time, slowly evaporating over timescales that dwarf human comprehension. And we'll continue our smaller dance here on this small planet, looking up at the stars and trying to understand the nature of reality. Both dances are beautiful in their way. Both are part of the same universe, the same cosmos, governed by the same laws. Thank you for joining me on this journey to the edges of reality, to the places where gravity becomes absolute. If you enjoyed exploring these cosmic mysteries with me, please consider subscribing to this channel. There are more wonders to explore, more mysteries to contemplate, more journeys to take together through the vast landscape of knowledge and imagination. Until we meet again, dear friend, sleep well. Dream of curved space-time and distant horizons. And remember that you are made of matter that once danced in the heart of stars, that you are part of this astonishing universe, connected to everything, including the strange and marvelous objects we've explored tonight. Good night, and thank you for traveling with me to where gravity becomes absolute.